So welcome back. We're now going to talk about the proof of convergence, right? So the idea is that you have some intuition about how this algorithm works. So let's now formalize it, right? Whether it will actually converge or not, right? So I'm going to first state the theorem, and before that I'll define something. So two sets P and N of points in an n-dimensional space are called absolutely linearly separable. And I'm just going to read out the definition. If n plus 1 real numbers w0 to wn exist, and you recognize these numbers or these variables as the weights that I want, right? So that's what I want to find. So of course the definition will contain these weights, right? So if such numbers exist such that for every point, right, and remember the points are themselves vectors, right? So this is a vector x1 to xn belonging to P. So every vector belonging to P satisfies this condition, and similarly every vector belonging to n satisfies the other condition, right? And this could be greater than or equal to 0, right? Okay, I've fixed the inequalities. So every point belonging to P should satisfy the greater than or equal to w0 condition, and every point belonging to n should satisfy the less than w0 condition, right? So if that happens, then the points are said to be linearly separable. That's just a definition. Now, so now here's the statement of the theorem, right? So if the sets P and N are finite and linearly separable, that just means your data is finite and is linearly separable. The perceptron learning algorithm updates the weight vector a finite number of times, right? So what does it mean? So you remember that in the algorithm, while not convergence, we are updating the weight vector. W is equal to W plus X in some cases, W is equal to W minus X in some cases, right? And the question was, what if this keeps toggling and then we keep updating the vector infinitely, or we never exit the loop, like the loop becomes an infinite loop. So this theorem is saying that will not happen, right? It will update it a finite number of times, right? So what is it saying? That if the vectors in P and N are tested cyclically one after the other, right? That's what we are doing. We're picking up vectors randomly for P and N. A weight vector W is found after a finite number of steps T such that it can separate the two sets P and N. Right? So that's what this is saying, that this will not go on infinitely. If your data is linearly separable, the perceptron learning algorithm will find a weight vector W after a finite number of steps, right? Now, how do you prove this? So let's look at that, right? So let's look at the proof of this. Okay, so I'll start with the proof. First, I'll talk about the setup. So if x belongs to n, right, it's a point for which the output is 0, then minus of x belongs to P. This is trivial because if x belongs to n, then it means that W transpose x is going to be less than 0, which implies that W transpose minus x is going to be greater than or equal to 0, right? So now what this observation allows me to do is that we can thus consider a single set P prime, which is the union of P and n minus. What is n minus? N minus is the negation of all the points in n, right? And now for every point belonging to P prime, right, which is the union of P and n minus, I want to ensure that W transpose P should be greater than or equal to 0, right? So this is just changing the notation. So earlier if I wanted W transpose P should be greater than or equal to 0, right? And W transpose n, which is n is a point which belongs to the negative set, should be less than 0, right? But now what I have done is from every n, I have constructed another P, right, which is just the negative of n. So now every point in my data set has the output to be plus 1, right, has the output to be P, right, 1, sorry, because I have just taken the negative of that point. So for whatever point, if for the original point, the output was 0, so for the negative of that point, the output should be 1, right. So I have just constructed this single set, which is a collection of all the points for which the only condition that I need to satisfy now is W transpose P should be greater than or equal to 0 for all the points in P prime, where P prime is as defined on this slide, right. So just a simple change, nothing great here, right. This will just simplify some of the some of the steps in the proof, right. Okay, so I'll start with the algorithm. So P is all the inputs with label 1, N is all the inputs with label 0, N is this negative of N minus is this set which contains the negations of all points in N, and now I'm defining P prime as the union of P and N minus, right? And now I'm going to initialize W randomly. Again, I'll have this convergence condition, and what am I going to do? I'm going to pick up a random P or random point belonging to P prime, where P prime is the union defined above. So what am I going to do till it does not converge? I'm going to pick up a random point P belonging to P prime, and for that point I'm going to check if the condition is not favorable, right? The condition should have been that the summation WIPI should have been greater than equal to 0. But if that is not the case, then I'm going to make an update, and my update is just going to be W is equal to W plus P, right? So notice that I don't need the other if condition, because now I have converted all points to points such that the label has to be 1. That means the only condition that I care about is that for all points, the dot product between W and P should be greater than equal to 0. If that condition is not satisfied, which is what this if loop is saying, then I need to make a correction. Right? So this simplified my algorithm. Nothing has changed conceptually. It's just that I have conveniently changed all the n's to n minus, and then that's why all my points in the data become positive points. That means for all of them the label is 1 now, and then in that case I only need to worry about one condition, right? That's what I have done. Further, for convenience, what I'm going to do is that I'm going to normalize all my inputs. I can do that, right? Whatever inputs I have, I'll just normalize them, and that does not change anything because my original point was P and I have normalized it, so it has become P divided by the norm of P. That's what normalization means. And if W transpose P is greater than equal to 0, then this is also greater than equal to 0. So it does not change anything with respect to the conditions. So it's a simple step which does not change anything conceptually for me. So I'm just going to normalize all the inputs, and that ensures that the norm of P is equal to 1, right? And this will help me in simplifying some steps in the proof. Okay. So, and now I'll define one more quantity which is W star. So that let W star be the normalized solution vector. What do I mean by that? I've started with the assumption, the proof says that if the data is linearly separable. So if the data is linearly separable, that means there exists some W, right? And I'm going to call that W as W star, such that that is the value which will linearly separate my positive points from my negative points, right? So some W exists, I'm sure about that, and I'm going to call that W star. It's just that I don't know what that W star is, but I can assume the existence of such a W star, right? So that's the W star that I'm going to use, right? We don't know what it is, but it exists, right? Now suppose at some time step t, we inspected the point pi, right? What does that mean? I have points p1, p2 all the way up to such some pm which are belonging to my set p prime, right? These are all the points, and at every point inside that loop, I'm going to randomly pick up one point, right? So that lets that point be pi. So I'm at the tth iteration of the loop, and the point which I have picked up is pi. Okay, and we found that the condition is violated. We wanted W transpose P to be greater than equal to 0, and suppose it's less than 0, right? Suppose the condition has been violated. Okay, so now what will I do? We make the correction that my new weight vector is going to be the weight vector at the current time step plus pi, right? That's what is the correction that we are going to do. Is that correct? Okay. Now if I'm going to make that correction, so now let beta be the angle between W and WT plus 1. Okay. Now what is cos of beta going to be? It's going to be this dot product. Okay. And why don't I have W star here, the norm of W star in the denominator? Because I had already assumed that W star is the normalized weight vector, right? That means the norm is equal to 1, so I don't need to write that in the denominator. Okay. So this is what cos beta is. Now let's just try to expand this, right? So now I'll now look at the numerator alone. Let me just get rid of some stuff here. So the numerator is W star, the dot product between W star and WT plus 1. Remember that W star and WT plus 1 are weight vectors, right? These are vectors. So I can talk about the dot product. And now I can just substitute the value of WT plus 1, which is nothing but WT plus PI, which is again, of course, a vector. It's the addition of two vectors. Now I'm going to open up these brackets. So I get W star, the dot product between W star and WT, and the dot product between W star and PI. Okay. Now I'm going to define a new quantity. So let me just explain something before I define that quantity. So I have the points P1, P2, all the way up to some Pm. Right? These are all the points which belong to my P prime. Okay. Now I can compute the dot product between each of these points and W star. Okay. I don't know what W star is, but I can define the dot product. I can say that this is the dot product, okay. And now what is dot product? Dot product is some scalar value, right. So for each of these, I'll get some value belonging to R, right, some scalar value I'll get. Now I can define the minimum of all these quantities, okay, fine. So let me call that minimum as delta. So what is delta? I have computed the dot product between W star and each of the points in P prime, and whatever is the minimum value, I am calling that as delta, okay. So what does that mean? That any of these quantities here are going to be, control Z, yeah, are going to be greater than equal to delta, right, because delta is the minimum value. So all these values are going to be greater than equal to delta. So that's how I'm going to define delta. So now with that definition, I can say that this quantity here is going to be greater than equal to this quantity. This directly follows from my argument that all of these quantities are going to be greater than equal to delta. So irrespective of which of these PIs I have picked up, P1 to PM, the W star dot PI is going to be greater than equal to delta. Hence the sum here is going to be greater than equal to the sum here, right, follows simply from the definition, right, where delta is the minimum dot product between W star and all the points that I have, okay. Is this definition clear? Okay. So now let's proceed. So now I can again for W T again replace it by the definition, right. So WT was again WT minus 1 plus some Pj. So at the previous time step I would have taken some Pj, right, and WT minus 1 I would have adjusted by adding some Pj. So Pj is again one of these P points that you see here. So again I will do that expansion. So let me just so this is what the expansion will look like. And now again this quantity, I know that this quantity is going to be greater than equal to delta, the same argument. So this quantity is the dot product between W star and one of these points, and if delta is the minimum of those dot products, so this quantity is going to be greater than equal to delta. So I can replace that by delta, and now I'll have 2 delta. Is that okay? And I can keep going like this unless till from T, I'll have T, T minus 1, T minus 2 till I reach W naught, right, and I'll have some multiplier K here, right. So now the question is, why is this multiplier K and why is it not T? T is the number of steps I have taken, right, but at every step, remember, I may not have made a correction, because for some PIs that I would have picked, the right condition would have been satisfied and I wouldn't have made a correction. So my K, the number of updates which I make, is going to be less than equal to T, right? That's why I have K here and not T delta. So K is a quantity which is less than equal to T, because every time I make an update, this bracket opens up and then I replace some quantity there by a delta. So this bracket will open up. That means this in many cases this Pj would not have been there, right? I would have not changed my weight vector. So this bracket will open up only that many times, as many times the condition was violated, and the maximum number of times the condition can be violated is T, because I have made T updates so far. So I would have made some K less than T updates. Is that okay? Less than equal to T updates, right? Let's see. Yeah. So we do not make a correction at every time step. So we make a correction only if this condition is satisfied. And so at time step T, we would have made K less than equal to T corrections. This is exactly what I had said. And every time we make a correction, we get a delta term here, right, in this equation, right? Because here I made a correction. So because of that, I got a delta here. Here I made a correction. So because of that, I got a delta again here, right? Every time I make a correction, I get delta. So I'll get K such deltas. Okay. So this is what the numerator looks like. Okay. Now, so far, we have that W transpose Pi is less than equal to 0, hence we made the correction, right. For the current point, this condition was, the unfavorable condition was satisfied, hence I had made a correction, and cos beta was given by this definition. Of that, the numerator is greater than equal to this condition, right. So the numerator is equal to this, and then I derived a series of things that the numerator is greater than equal to 0. Okay. Now I am going to focus on the denominator. Okay. So the denominator is the norm of Wt plus 1. So the square of the denominator will be the square of the norm. Okay. Now again Wt plus 1, the norm, I can first I'm going to expand Wt plus 1, which is Wt plus Pi, right. So Wt plus Pi norm square, right, that is what this is, and the norm is just the dot product of the vector with itself, right. So Wt plus the square root of the dot product, so now this would be Wt plus Pi and dot product with Wt plus Pi. Okay. Now again I'll just open up the brackets. Okay. So I get the square of the norm of Wt plus 2 times Wt dot Pi, okay, plus Pi square. And I had assumed that the Pi's are normalized. So the norm of Pi is going to be 1. So I'm just going to replace that by 1. Okay. And I'm going to do something else also. So how did I get from here to here? Because of this condition. I know that Wt Pi is less than equal to 0. That's why I am here, right? And if that is the case, then 2 times Wt Pi is also going to be less than equal to 0. That means this sum is going to be less than or equal to this sum. Let me just get rid of all the marks. So this sum, okay, has a quantity which is negative. Okay. This sum does not have that quantity. So it follows that this sum is going to be less than or equal to this sum. Is that okay? Because it's just this sum plus a negative quantity, so it's going to be less than or equal to. Okay. Now the next step of course is to replace Pi square by 1 because Pi's are normalized. This was a simple assumption I had made. Now by induction again the same thing will happen. I'm going to now, I started with Wt plus 1 and I ended up with this. Now I'm at Wt, I'll again do the same step there itself, right. And what will I get? This is going to be Wt minus 1 plus 1, right. This will again happen. This 1 which I had come here, again the same thing will come here and I'll get 2. And how many such 1s will get added? The same argument, as many times I make an update, a 1 will be added, right. Where is the 1 coming from? The 1 is coming from this quantity. If I made an update, then I had added a Pi. If I had added a Pi, then I'll get this Pi square term and I'll get a 1 there. So again here I'll have K, right. I'll keep simplifying this and I'll get to W naught square plus K by the same observation that we made about delta while dealing with the numerator. Okay. So now we have the numerator is greater than or equal to a certain quantity and the denominator square is less than or equal to certain quantity. So now these two conditions combined with the definition of cos beta will give us the condition that cos beta is greater than or equal to this quantity. Right? So I have simply substituted the numerator and I have substituted the denominator, the simplified denominator, and this would be greater than or equal to because the numerator is greater than or equal to this quantity and the denominator is less than or equal to this quantity, right. So the numerator is greater than something, the denominator is less than something. So if I put the numerator over the denominator, then the end result would be that cos beta is greater than or equal to this quantity that you see here, right. So now here you have a k in the numerator and a square root of k in the denominator. So which means I can roughly say this cos beta grows proportional to square root of k, right. And what is k? K was the number of times I have updated my weight vector. And this is the quantity that I wanted to handle on. This is the quantity that I wanted to show was finite. I wanted to show that k cannot tend to infinity. Okay. Now cos beta is going to be greater than or cos beta is going to grow proportional to square root of k. So now as k increases, cos beta will increase, right. Now if k becomes arbitrarily large, if it goes to infinite, that means my algorithm is not converging, it's keeping on updating. Then what will happen to cos beta? Cos beta will keep on increasing. But can cos beta keep on increasing? No. Cos beta is bounded between minus 1 and 1, right. So cos beta has to be less than or equal to 1. So cos beta cannot grow infinitely. That means k cannot grow infinitely. K has to be bounded by a maximum number. Hence we have shown that the k is a finite number. So if the data is linearly separable, right, that means after a finite number of iterations, the perceptron learning algorithm will converge. So although in our toy example, it does not seem intuitive, right? That's easy to build this intuition that, okay, for one point I changed it, for the second point again I changed it, why were these updates not counterproductive? So now we have a proof which says that the number of updates you will make will be finite if the data is linearly separable. Okay? So that's what the perceptron, that's what the proof for the perceptron's learning algorithm says, right, that it will converge. Okay, so now coming back to our questions which we had started out. So what about non-Boolean inputs? Yes, so real valued inputs are allowed in perceptron. Do we always need to hand code the threshold? No. Now we can learn all the parameters, not just the threshold W0, but also W1 to Wn. Are all inputs equal? No. Now perceptron allows weights. What about functions which are not linearly separable? So this is still not possible with a single perceptron because we have seen that the boundary is linearly separable. The previous proof was also that it will be able to find the weights only when the data is linearly separable, right? But we'll see how to handle this. Right? That's what this course is about, that what if data is not linearly separable. Okay. So I'll end this module here and we'll talk a bit more about linearly separable functions.